This video is an introduction to the Class D Power Amplifier Lab, Lab 11, which is Chapter 37 of Applied Analog Electronics. Now, the basic part of this lab is to build a Class D power amplifier. I'm not going to tell you exactly how to do that. We've had several previous videos, several previous chapters of the book, which talked about the various components that go into making up a power amplifier. Your design goal is to make a power amplifier that drives your loudspeaker with about 3 watt peak power. That's quite a bit more than if you just use the preamplifier that you did in Lab 9, because that preamplifier had a current limit of about 23 milliamps. And with a 23 milliamp limit and an 8 ohm loudspeaker, your maximum power is only about 4 milliwatts. So we're looking at something that's 750 times more powerful than that. And you're not going to be able to do that with just op amps. You need to be able to get much larger currents. Now, the design goal that I've given you there, that you've got to get at least 3 watts peak power into your loudspeaker, is not a sufficient design goal. So one of the things you have to work out in making your lab, doing the initial design, is to figure out in detail what the actual specs are for the amplifier you're going to make. How powerful is it going to be? What frequencies is it going to be? What sort of load are you driving? Are you driving just an 8 ohm loudspeaker, or is your loudspeaker something different? What are you taking as input to the amplifier? All these things are part of the design process. And it's quite typical when you've got a real engineering design problem in the real world to be given a design spec that is totally inadequate for actually doing a design. It's just sort of a vague statement of, we want something that does X, where X is really, really vague. And part of the job of an engineer is to nail down, well, exactly what is it that you need? What are the constraints? Or what are the goals? And sometimes your customer won't know. And you either have to make some good guesses or give them some suggestions and say, well, if we do this, then we have these trade-offs, and let them make choices given some knowledge about what those choices entail. Okay, so design constraints on this one, in addition to whatever parts you've got in your lab kit, you can also use the Analog Discovery 2 as both a power supply and as a triangle wave generator. Okay, so what are the parts you're going to have to do? Well, one of the first things you have to do is come up with a block diagram, and that means you've got to come up with what are the inputs and what are the outputs of your system, and what are the main criteria on the various signals you've got there. What do you know about them? So what frequency range do you want to amplify? Are you trying to amplify something for a voice range, or are you trying to amplify something for a music range? Generally, when people are doing voice, they use a much narrower bandwidth when they're trying to do music. And for voice, you tend to emphasize the part that carries the information in speech. So 200 hertz to 5 kilohertz is often plenty for speech. But that's not very good for music. You'll lose the bass, you'll lose a lot of the timbre that comes from the higher harmonics. So depending what your goals are, you have to figure out your frequency range. Power amplifier, how much power do you really need out of this amplifier? And that's going to determine things like, what's the power supply voltage have to be? And you also have to look at things like, okay, I've got a component here that's going to do part of the work for me, this preamplifier that goes from the microphone to the input of the power amp stage. What's the output of that preamplifier? How much voltage? How much current? Where's the voltage centered? All those things are important in doing the design, and you should, lay out what your different blocks are of your design and what all the signals are, the interfaces between those blocks. There's a tendency for electrical engineers in general, to say, well, these are the parts of my design, here's my blocks, and not to pay nearly enough attention to what is the connection between the blocks. And that's why I'm insisting that on all your block diagrams, every signal be labeled with all the information that's critical about that signal. And that could be frequency range, it could be voltage range, it could be current. It depends on what it is that you need to know for the blocks on either side of that that signal. What is this thing output? What is this thing input? Okay, so once you've got the constraints of your overall design, you end up with things like, okay, if you're going to do a Class D amplifier, you're going to be using pulse width modulation. What's your PWM frequency? And you should probably have it be at least 3 times as high as the highest frequency you want to amplify. I mean, Nyquist's theorem says it has to be at least twice as high, but it's very hard to make the filter that separates the PWM from the signal if you've only got that little narrow range. So making it at least 3 times as high makes it a little easier to design your filters. Now, you do have some constraints on your PWM, because if your PWM frequency gets too high, then the field effect transistors will be spending a lot of time switching, and a greater portion of their time will be doing that switching, and so you get loss of efficiency. So generally you want to use the sort of the lowest PWM frequency that you can easily filter out. And again, there's not a correct answer here. This is a design problem. There are trade-offs. Make a case for the PWM frequency you choose. Make sure that it's consistent with the frequencies you're planning to amplify, and that your transistors will switch at the frequencies you've requested. Make a block diagram of the whole thing. Label a function of every block, and I do mean the function and not the part number. The function of a block is what it does, not how you implement it. And a lot of people have been doing things like saying, oh, this is a, and then putting a part number. That's appropriate for a schematic. For a schematic, I do want the part numbers. The part numbers are essential to a schematic. But a block diagram is about the function of the blocks. What do they do? Not how do they do it, or how much they cost, or where you get them from. It's what their function is. And that's the essential thing that makes it a block diagram. Label the signals between the blocks, write down any DC or AC voltage levels that are appropriate for that. Make it so that somebody can look at a block and see, okay, this is what the block is supposed to do, these are its inputs and these are its outputs, and from just that piece of the block diagram, just the one block and the signals on either side, can design the block. If you haven't got that sort of information in your block diagram, you're missing something. Okay, if you have to do any DC voltage level conversion because something is centered here at 0 volts, something centered here at 1.65 volts, something centered here at 2.5 volts, make sure that any of those level conversions, stuff like that, have functional blocks that do the conversion. You may not need to have any such blocks, but pay attention to that. That's one of the reasons for having the signal levels and stuff all very explicit there, so you can see, oh, there's an incompatibility here. This is assuming it's got an input centered at 2.5 volts. This thing's got an output centered at 1.65 volts. Inconsistent. Make sure that everything is consistent, and you can tell the consistency just from the block diagram. Okay, once you've got your block diagram, then draw a schematic for each block, and you can draw these things separately. Now, one of the blocks is going to be your preamplifier, which you did from lab 9, I guess it was. Include that schematic too in your pre-lab here, because what you want to have is that every block has its implementation described here. Now, some of them are ones that you don't have to rebuild because you already built them, like the preamplifier, but include it anyway so that the report, when you're done, is a complete report, and people don't have to go say, okay, I can build all this thing except for this chunk here that's missing. I don't know how to do that. And, oh, well, we never gave you that report because we didn't know you needed it. So make sure that this report, both your pre-lab and your lab report, are complete, that they do not have to go out to the book, out to the previous lab reports in order to get the information needed in order to do the design, to check it, to make any changes that are needed in the design. Because remember, the purpose of a design report is to help future engineers, if they have to redesign what you're doing because some specification has changed, to say, okay, I understand the design, I can figure out what all the pieces are, and I can find where to change it to make it now meet the new set of specs. So your design has to be complete, your design report has to be complete in that sense, that a future engineer can see how you did everything, why you did it the way you did it, and make changes if some specifications have changed. Okay, on your schematics, make sure you put in the part numbers. I get very tired of seeing something that says, oh, this is a field effect transistor. And it's, well, which one? There are thousands of different field effect transistors. And it makes a huge difference in how well the circuit's going to work, whether you've got the same one or not. And somebody might say, well, this one's no longer available. What's the replacement for it? I need to know which sort of transistor it was, why, what parts of the design were affected by that choice of transistor. So I need to know what the transistor was. So all the part numbers should be on the schematics. That includes microphones, transistors, inductors, because the series resistance of the inductor matters. For the capacitors, because we're using very cheap ceramic capacitors, and for the resistors, because we're using very cheap metal film resistors, we don't have part numbers for those. But it'd not be a bad idea to put down what the tolerances are, like that we're using 1% metal film resistors. So as much information as you can so that somebody can actually go out and make a bill of materials to put this thing together from your schematic. Okay, once you've done all that stuff, one of the things you have to be concerned about is, well, what is your power supply going to be? You've got data sheets for your PFET and your NFET, and you'll have to find out which ones are in your parts kit. That varies from year to year. So look for it for this year's lab. What parts were you given? And I've listed a couple parts in the book for ones we have used in the past. There's no guarantee that you'll have those this year. So take a look at the parts list for this year. Make sure you've got the right parts on your both on your schematic and in all your calculations you do. You can now figure out how much power you can safely have them dissipate, how much current they could safely handle without a heat sink, based on how hot they can be allowed to get. Now this can be a little bit difficult because usually on the data sheets they specify things with a heat sink. Now sometimes you can get a lot of information because, like for instance, if we're using the SOT23 surface mount packages, most of those packages have very similar characteristics. And so if you can't find the data for the particular transistor you've got, you might be able to find it for a generic SOT23 package. Look at the gate voltages you need to turn the NFET or the PFET fully on. It's not just the threshold voltage, but a little beyond that before you actually turn it on fully. And this information is all on the data sheet, but you may have to spend some time interpreting the data sheet to make sure, okay, can I turn this thing out at 3 volts? Can I turn it on at 2 volts? Do I have to go all the way to 5 volts to turn it on? These things make a difference. It'll affect the power supply, the minimum power supply, the maximum power supply you can use are all going to be affected by the characteristics of your transistors. So you have to look at the data sheets and figure out what you're doing with it. Okay. And then take a look at what you would do if you wanted more power. So think a little bit about ahead. I asked you to deliver at least 3 watts. What if you need to do to 10 watts? What would have to change? How much would you be able to do it with the parts you've got, or would you need different parts? What voltage and current do you need from the power supply in each case? What are the limits on the other components? Okay, you've got comparators probably, you've got your preamplifier which has got op amps in it, you may have some inverters in there to act as digital amplifiers for the PWM signal. What are the limits on each of these devices? What limitations do those put on your power supply? Make sure that everything is consistent and document it. Don't just come up with a correct answer, because there is no correct answer. Come up with justification for the choices you made and document them. So if you decide, hey, I'm going to use a 3-volt power supply, why? I'm going to use a 6-volt power supply, why? And what are the consequences of the choices you made? And if there's a range, you say, well, anything from this to this will work. Explain it. And basically, once you've got all the pre-lab stuff done, your design should be done at that point. And that's where, if this was a just on paper sort of course, you'd be done. Here's my design, I'm done. Now I'm going to ask you to build it, test it, because designs are never done just when you've done all the paperwork, you've got to then make sure that the design actually works. And when you're building the design, start from the beginning. Start with the preamplifier. Okay, preamplifier, you already tested that in previous lab. Test it again. Make sure it's still working. If you got the output, and make sure that the voltage range is what you thought it would be when you did your design. So starting from the microphone, the preamplifier. Once you've got those working, what's the next stage? Probably a comparator. Is your comparator doing the right thing? Are you getting the PWM signal you want? Quite likely you're not, because you'll probably have made some mistakes in your thinking about the relationship between the triangle wave voltages and the output of the preamplifier. Very common mistakes for students to make along those lines, and you'll have to think through, okay, why isn't this working? What isn't it doing what it's supposed to do? One warning about that, if you're using just one of the two comparators in the dual comparator chip, make sure that the other comparator always has a constant output. So the unused comparator should not be sitting there with unused inputs, because those two unused inputs may be very similar to each other, and small fluctuations can cause the output to switch back and forth. And that output switching back and forth can couple noise over to the comparator you are using and really mess things up. I've had that happen to me. I've seen it happen to a lot of students. So when you're not using a comparator chip, tie the two inputs of it to opposite power rails so that the output is well defined and won't change. You have a similar thing actually whenever you have unused op amps. For unused op amp, it's usually recommended that you tie the two inputs together so that they're both the same. For comparators, you want to tie the two inputs to be different so that the output is well defined. Okay, once you've got your PWM signal working, see if you can drive your power FETs with it. Once you've got your power FETs working, make sure that you can if you've got an LC filter there, make sure that the LC filter is working, make sure your loudspeaker is working, sort of build it up one step at a time. And if you do it testing one step at a time, it's much easier to debug, because you can say, I know it's working up to this point, so just this one new thing I added must be where the problem is. If you try and build the whole thing all at once and it doesn't work, then it's really hard to figure out, well, why isn't it working? Is the whole thing wrong? Or is it just some wire missing, some misconnection? And it's very hard to debug if you've got a huge system to debug. You always want to be able to subdivide it into pieces. And this particular design is easiest to work sort of from the input towards the outputs, and checking at each stage, is this thing doing what I want? And then when you're done, demonstrate it and write it up. Most of your writing should be already finished at the point when you started doing the building. So you had all the design work done at that point. You may have had to rewrite some of that stuff because you found an error in your design as you started doing your testing. But a lot of students have actually found that if they did a good job of the design and really paid attention to what they were doing when they were doing the design, that the construction testing goes fairly quickly. It's not guaranteed. Things can always go wrong whenever you switch into the real world. But it's certainly much more likely to go well if you've been careful in the initial design. So get your demo and write-up done, and you're done with the lab. Now, there are a lot of bonus lab parts available for this one. Don't try them until you've got the basic fundamental circuit working. There's no bonus points if the thing doesn't work. So make sure you've got the fundamental basic circuit working before you attempt to do any bonus stuff. And the bonus stuff can be all kinds of different things. Measuring the current into your loudspeaker, taking, instead of a microphone input, taking output from an MP3 player or a phone or some other sound source. This may require you to think a little bit about signal levels and stuff, because you may even want to measure the signal levels coming out of your phone before you do anything. You could try doing a design with a dual power supply. We've been doing everything for this entire course with a single power supply. Loudspeaker is something you can do with a dual power supply. You can then do just a single CMOS and one N FET, one N PFET rather than an H bridge. But because your voltage is going to be more limited, you may have run into some problems here and not be able to get as much power. But it's something you can think about and try. You can use the network analyzer to characterize your amplifier, either just the power stage or the entire amplifier from the microphone input all the way to the loudspeaker. You can characterize the acoustic behavior of the LC Filter Plus loudspeaker by using the network analyzer, using a microphone to listen to the output of the loudspeaker. So you're looking at not just the electrical behavior now, but the acoustic behavior, what's happening out in the air. You could design your own triangle wave generator instead of using the function generator on the Analog Discovery 2 for the triangle wave. This is a little bit trickier. I mean, there is the previous chapter of the book that talks about it. This is definitely a bonus thing. It's not something I expect very many students to do. There's a different Class D amplifier design that uses feedback from the H-bridge rather than using a triangle wave generator and a comparator. This is trickier to get to work. I don't like the design usually as much, but it's an interesting alternative. And again, there's some discussion of that in the Class D amplifier design chapter. And you could also look at trying to get higher power, because you can put, depending on what loudspeakers we managed to get this year, you can probably put up to 10 watts into your loudspeaker, and that may require a higher voltage than some of the components that we've got can take. Particularly the inverter chips and the op-amp chips won't take the higher voltages you might need for that. So you might want to think about how would you do that? How would you handle something where you use higher voltage for the power supply than what some of the components can take? So lots of possibilities for bonus points. And there's probably other things here I haven't thought about. I'm not suggesting that you do any of this bonus stuff, but if you're looking for bonus points, there are a lot of possibilities on this lab. So have fun doing your design and have fun testing it. This lab is one where people are often quite surprised by how well the whole thing works, when they finally get it working, of course.